So I'm recording this because one student, and zooming it because one student requested that I do it for what it's worth. So let's start with the results. Okay, from the last round. So no change at the top. Still Disco and Ratatouille. Although if you look at the plot, Disco does not have the big lead as they did before. So everybody's making money. Everybody's over 900,000, so that's a good thing. We did have some big movers. The biggest, by far, CD's nuts. Karmic, for sure. They could drop below 13. I'm sure they would have. Also some big movers, the big three. Rack Mamba, probably the biggest move up. Rack 2.0 Future. The English major team, all moving pretty well. All right, so we've seen a lot of changes in just a week. Okay, this is just the assets from period 1 to period 2. You can see that who was in second place? Ratatouille. They've kind of caught up a little bit to Disco. Everybody went uphill, although the slopes obviously vary quite a bit. Okay, here's the sales versus price for the first 2 periods. Orange being the first period, blue being the second period. Obviously, everybody who set the price is above 80. I just changed the price to 80 because that gives 0 demand. And again, kind of, you know, it looks a lot like what happened in the practice round as far as I can tell, for the most part. Okay, sales versus price by team. And I don't know, whoever these guys are, they set a really low price for some reason. Stock price versus assets. Again, it's a fairly strong relationship, right? So assets are not the only thing that drive your stock price, but they're certainly a major component of it. So just stock price by team, by period. Some going down, some going up. However, Disco obviously has a huge stock price advantage at the current time. Probably accounts for their first place standing. Here we have my holdings page. So basically the idea of this is to see, aside from the stock that companies hold in themselves, how much money have they invested into the market in other teams, whether it be buying other teams or shorting other teams. You can see there's still the big three is still a big player. Racks on Racks and Crackheads have also invested a significant amount. Oh, I forgot these guys here. Rack It Up too. Stack and Racks is in for 20, and then there's 1, 2, 3, 4, 5, 6, 7 teams that have essentially done no stock market investment. You can see cash on hand here. Right, so I don't know why I highlighted the big three and Ratatouille. I highlighted them because their cash is lower than most. What I should have done is highlighted teams like Stack and Racks or CD's Nuts, even more, who are sitting on loads of cash. Stack and Racks, right? So if you want to keep that cash under your pillow or under your mattress, that's fine. I think you may have learned in your business classes, I'm not sure, you tell me, but keeping money under your mattress is typically not the best idea. Construction projects, I don't think there's any change from last time. Finished goods inventory, I thought this was interesting. Everybody had zero finished goods inventory except for the crackheads. For what it's worth. Raw materials. A couple teams have a fairly significant supply. CD's nuts, they still own a lot. They owe a lot of money, which is, which is why they probably still have a lot of cash, right? Basically, they borrowed money so they could put it under their mattress. If that makes any sense, which of course it doesn't. Earnings per share, all positive. In fact, almost all greater than $1, except for CD's nuts. They account for their dramatic slipping in the ratings. And insider holdings. Just note that Rack Shack has purchased the last time 500 shares of their own stock. They're purchasing 2,000 more shares next period. Shack and Rack is also purchasing some of their own stock. And this is just the, this is just the sales numbers. So a lot more kind of normal. In fact, this is the most normal I've ever seen in many years, where most of the companies are selling right around the 3,000, 4,000, 5,000 units number, which is what their basic capacity is at the moment. Rack and Roll sold 0. I assume that's because they were burdened with a lot of back orders they're trying to get rid of. Okay. Any questions on the game? All right. So today's lecture is about forecasting. We're actually going to talk about it for 2 weeks in a row. So this set of PowerPoint slides for this weekend, that's about halfway through, and then we'll finish next week. Today we're talking about model-based forecasting methods. And the main tool we'll be using in here is called regression analysis, which I'm sure you've seen before, maybe a little bit at least. Next week, we'll talk about what are called forecasting methods. These are things based on smoothing, the simplest of which is a moving average. Moving average is a very simple thing that's not a model, right? But today is actually probably more interesting than next week. We're talking about model-based forecasting methods. I will also say this, so for the first 5 weeks or so, however long it's been, we've been using Solver. Today we'll be using some of the data analysis, in particular the regression abilities of Excel. Okay, so forecasting, I think everyone knows what it is. We're trying to predict the future behavior of some process or variable. I should say some random process or random variable, trying to predict the future behavior based on past data. All right, so forecasting is fundamental to business planning. Pretty much every business decision is based upon forecasts. Right, so probably the 2 most important forecasts in business are you need to forecast the demand for product and the ability to forecast prices of various commodities. So in the business game, it'd be very nice if you knew what your demand was going to be in the future. It would also be very nice if you knew what was going to be the price of raw materials, for example, right? So I mean, why forecast demand, right? So I mean, you know, if you know what demand is going to be, then you know how much raw material to buy, you know how many workers to schedule, you know how much inventory you should ship to your warehouse in Denver. All of these decisions are fundamentally based on the need to know what your demand is going to be. Okay. Even long-term decisions, right? Should I build a new plant? Decision like that is based on a long-term forecast of what's going to happen to your sales or your demand. Okay. Basically, the more accurate you are, the more accurate your forecast is, the more efficient you can be. Right? If you have a forecast with huge potential error, with huge confidence interval, shall we say, you really don't know much about demand, and so you have to plan for the worst case, and you end up being less efficient than if you had a really accurate forecast and you could get everything right. Okay, so what are we forecasting? We're forecasting what are called time series. The time series is the measure of some particular thing at intervals in time. So here's a good example. This is monthly Australian red wine sale. How much red wine is sold each month in Australia over a period of several years. All right? This is our historical data, and we will be trying to forecast what's going to happen out of this. All right, so if you look at this time series, there are a couple of things that should appear right off the bat. One is that there's an overall trend upward over time. The second is that it looks like there's some seasonality. Right, so if you look at those, there's like a bottom every so often. If you count the points, you see that bottom occurs every 12 months. Same with the top, right? So there's a monthly effect, there's a seasonal effect that affects this time series as well. If you were to look at it even more carefully, it might not be obvious, but there's sort of, you know, like a cyclic pattern that has a certain amplitude. And as time goes on, that amplitude gets bigger, right? There's more spread over the period of a year at the end than there is at the beginning. These are all patterns that we can see in this time series, patterns that will allow us to forecast the future values of this time. So it's the yearly level of Lake Huron. Not sure I see much of any pattern in this one. It's another example of a time series. Monthly polio cases. I put this in here merely mainly to show that sometimes we're trying to forecast things that have integer values rather than real numbers. But typically we're forecasting real numbers. Monthly traffic injuries in Great Britain from 1975 till, I don't know, a few years later. So again, you see that there's clearly a seasonal or a monthly pattern to traffic injuries, which I didn't know. It's kind of interesting. There was actually a reason for this time series. Right around where my cursor is in time, Great Britain had instituted a new law, new traffic safety law. And they used this time series to attempt to show that it had actually affected traffic injuries in a positive way by reducing them. Population of the United States over a 200-year period. Another time series. This is a very famous one. You don't know what a lynx is. A lynx is kind of like a bobcat. This time series looks to be seasonal. But interestingly, if you actually count the points between the peaks, they're not evenly spaced, right? the number of, the number of years between the peaks is not always the same. So this is actually behaving like a second order differential equation rather than a periodic model. There are forecasting methods for model things like this. This is an example of two different time series. The daily closing price of the Dow Jones Index in the United States and the All Ordinaries Index, which is basically Australia's version of the Dow Jones. And if you look at them, it seems that they kind of move in the same way, right? So it makes you wonder if you couldn't use one to forecast the other, right? If I know what the All Ordinaries closed at today, which for them would have been early in the morning, that might help me predict what the Dow is going to do today. Who knows? Okay, so those are just examples of time series. These are the kinds of things we're forecasting. So there's two basic fundamental laws of forecasting. The first is that we assume the future will behave like the past. We're using past data to predict the future. And if the future does not behave like the past, how the hell can we forecast? The answer is we can't. So for example, if I had this time series here and I was trying to forecast into the future, which is this green area, right? You can imagine where your forecast might be. But what if this is what actually happened? Given that data, is there any way you could have seen that coming? The answer is no, of course not. Right? So if the future does not behave like the past, none of this will do you any good whatsoever, and you'll be way wrong. Okay? The second law is that even if the first thing is true, if the future does behave like the past, there's no way to have a completely accurate forecast. Right? There will always be randomness, there will always be unknown factors that make it impossible for you to predict with 100%. Right? That's the other thing. Okay, so there may be some so-called signal in there. There may be a trend you can exploit. There may be seasonality you can exploit to predict. But there will also be a random noise component in there, and that is something you can't do anything about. You just have to live with it. You know, the random noise component is inherent in any time series, and if it's a big random noise component, then your forecast will be less accurate than if it's small. There's a limit to accuracy. Okay. It's an example where each consecutive data point is distributed according to a normal distribution with mean 0, and all the points are independent from one another. Right? So these are just normal 0 sigma squared data points. And if you tried to forecast into the future of this time series, your best forecast would simply be 0. I mean, there's no other pattern you can exploit here from any pattern, right? So this is a pure noise component. This is what a pure, in double E they call it white noise. This is a white noise signal, and it's unforecastable other than just saying 0, right? I got a camera here. Maybe I should stay in front of it, huh? Okay, so as you hopefully learn taking statistics, it's one thing to have forecasts or to have estimates of things, but the whole value of statistics is that you not only you have an estimate, but you have some idea how accurate that estimate is. So that's important in forecasting as well. And so we usually want to have an estimate of the accuracy of the forecast. So not only do we have forecasts into the future, but we have some idea how accurate they are. And perhaps we can even put confidence intervals on those forecasts. We know, there's a good chance, a 95% chance that the true demand is going to be between these limits. And knowing those limits is probably as important as knowing the estimate itself. Okay? And we use various ways to estimate the errors, or the variance, if you will. So it kind of works like this. Kind of some notation here. So x sub t is the value of the time series at time t. And this thing here, x hat, the hat indicates its forecast. This is x sub t hat, means it's a forecast of x of t, but that forecast was made at time t minus k. So k time units ago, we made a forecast for this period. This was the forecast here. The forecast for period t made at time t minus k. Right? And then we have our actual value at time t. So the difference is the forecast error. Right? So it's the actual minus the predicted, basically. And then you can square that and add it up, and that gives you the mean squared error. Well, actually, you'd have to divide by n. I forgot to divide by n, but it's called the mean squared error. Or sometimes people look at the absolute value rather than the squared. Measure of forecast error. Sometimes they square it and then take the square root. That's called the root mean squared error. So basically, the root mean squared error is an estimate of your standard deviation of your forecast, right? How much error you can expect. So it's good to know what kind of error you're going to expect. Okay, just to kind of reiterate, suppose you forecast next month's demand to be 700, right? Well, it matters what the error is. It could be 700 plus or minus 5 units, or it could be 700 plus or minus 300 units. Right, so if you have to produce ahead to meet this demand, like you do in the business game, in this case here, you'd have to probably produce close to 1,000 units to make sure you met the demand. And of course, you run the risk of having a lot of extra inventory left over. Whereas if you knew really accurately what your demand was going to be, then you wouldn't have to worry about those issues, right? So again, the more accurate the forecast, the more efficient your decisions can be. And the more money you can make. Okay, so that's kind of the end of the introduction. We're going to talk about basically 3 approaches. Well, actually, two main approaches. First being trend and seasonal decomposition using regression. And then we're going to talk about the time series methods, particularly what are called ARIMA. It's autoregressive integrated moving average models, which, if you're at all into this kind of thing, I think you'll find these to be really cool, these ARIMA models. And next week, we'll talk about forecasting methods. Okay, so just, I'm sure you've all seen linear regression, right? You have 2 variables in this case. This is for the IBE class in 2013. We have the fall GPA and fall 09 GPA and the spring 10 GPA. Each point represents 1 student. And if we knew their fall GPA, we're trying to predict their spring GPA, how would we do it? Well, we might be tempted to fit a line to this data and use that line to predict for future classes, right? All right, but which line should I use? How do I figure out what's the best line that fits this data? That's what regression does for us. So basically, we're looking to build a linear model with an intercept and a slope. So x is the independent variable. In this case, it's the variable we will know ahead of time, the fall grade point average. And y is the dependent variable, spring GPA that we're trying to predict. You want to have a linear model that says I take my fall GPA and I plug it into this model with the intercept and a slope, and that will give me my prediction for the spring GPA. Right, so the intercept and the slope, beta 0 and beta 1 are unknown coefficients. And we want to find the values of the intercept and slope to get the best fitting line. How do we define best fitting? Well, here's a particular line. We take the distance between each data point and the line. And note that that would be our forecast error, right? The actual value is the blue point. The predicted value is the value on the line at the same value of x. So we take these, the difference between actual and predicted. Mathematically, it's given by that. Y sub I is the actual. Beta 0 plus beta 1x is the predicted. We take the difference, square it, add them up. And we're trying to find the values of beta 0 and beta 1 that minimize the sum of the squared error. You can find the optimal values of beta 0 and beta 1 by calculus. We take the derivative, set them equal to 0, do some work, and you come up with the optimal estimate. Okay, predict the value, actual value. Now, I think it would be good for me to do some examples. How we actually do this in Excel. All right, so here's some data from the class of 2013. We have their spring 2010, spring 2010 GPA, fall. They also have their academic index. That's something admissions uses. Their high school rank, their math SAT, their verbal SAT, and the number of AP credits they have. Right, so if we were trying to predict their spring GPA, you might use all of these variables, but for the time being, we're just going to use the fall GPA. All right, so here's sort of the nitty-gritty details. So again, we go to data, but instead, oh, what the hell? Data. Oh, crap. I'm on said Shields ID, and we haven't installed Solver or the tool pack, so let's do that. Let's see, add-ins. How did I do this before? Go back. That's how I do it. Got to attach the analysis stuff in Golden Solver. Okay, there it is. Now instead of using Solver up here, we're going to use data analysis. We're going to go down to regression. Okay, so we have to put in the Y and the X. So the Y, that's what we're trying to predict. Put in this range of spring GPAs we're trying to predict. And then for the X, that's what we're using to predict Y. So that's the fall GPAs. We have labels in our column. We hit OK. Right? And so it gives us our regression output. Okay, so a few things are worth pointing out. Okay, this right here, these are the estimates of the slope and the intercept. That's where we would get our model. R-squared gives us some idea of how good our prediction is. Basically, you can think of it as a measure of variance explained. About half of the variation can be explained by this model. Our variance of our prediction will be About half of what it would have been if we'd have just used the mean as our prediction. And the p-values tell us whether these various things are helping us predict it all. So if you think of a hypothesis test, beta 1, beta 0 helps us predict or doesn't. H naught beta, the slope beta 1 helps us predict. And that's the p-value of the test. So if that's a small number, that means it's helping us predict, right? If there's no hypothesis, it doesn't help us predict, then we reject that with high probability. Right? With intercept, it's only a 0.04 p-value, but it's worth having. And then the slope is helping us a bunch, right? It's highly significant in helping to predict. Okay, so that's our model. These are our intercept and slope. So I might come back here. Those are the intercept and slope. It allow me to have a predicted value, right? And so the predicted value would be equals intercept plus the slope times the fall GPA. Right, and then I want to make sure I put in dollar signs there. Dollar signs, so I keep the same. I drag it down. Okay. Now I can have a scatter plot. And then my bad. Okay, so hopefully I don't have this backwards. This is my predicted values based on the fall GPA. These are the actual values. If I copy and paste it, right, it now shows the data values and then the line that fits the data. Point being, you can see it fits pretty well. This is one of the things that you have to do for the exercise. Okay. So you can use simple linear regression to fit. You don't have to, it doesn't have to be just a line. For example, we could fit a model that looks like this. Y equals some intercept plus x squared, or the sine of x, or ext of x, right? You can do all that the same way, using the same exact thing in Excel. Okay, so for example, here's the fall 09 GPA. All I did was I took that and squared it, right? These are just the fall 09 GPAs squared. So if I wanted to fit a model to use the x squared values, it would be really simple. I would just pick this column instead of this column for my x variable. In other words, go to data analysis, regression, have the same y value, but now my x values are going to be these fall GPA squared values, right? And I can just run that regression. Or I could have another column that's the sine of the GPAs, and I could could fit that model as well. But basically, all of these are simple linear regression models that you can fit, right? I mean, you look at the plot of your data, and if instead of the cloud appearing to be like a straight line, it looks like a quadratic, then you can fit a quadratic model, right? Okay, the reason why these are called linear regression models. So the model is nonlinear in the sense that I have a squared here, a sine here, an exponential, right? But in terms of the unknown variables, we're trying to estimate the beta 0 and the beta 1. It's linear, right? So here, the x squared, the sine of x, e to the power x, those are constants, and the unknowns are the beta 0 and beta 1. That's why we call it a linear regression model. It's linear in the unknown parameters, if you will, beta 0 and beta 1. Okay. So we talked about the idea of using not only fall GPA, but also SAT scores and other rank indexes and stuff, all of those variables at the same time to try and predict spring GPA. That's what's called multiple regression. So now we're looking at a model like this, where we're trying to predict over here the spring GPA. We have an intercept. X1 could be the fall GPA, X2 could be the SAT math score, X3 could be the SAT verbal score, and we're trying to come up with a model that looks like this. All right? It's called multiple linear regression because we have multiple variables we're using to try and predict y. Let's skip all the math. Bottom line is you can find the optimal estimates that minimize the sum of the squared error. In other words, estimates for beta 0, beta 1, beta 2, beta 3 by the exact same process. Take the derivative, set it equal to 0. It becomes a matrix issue, but basically this is what you get when you solve that calculus problem. Yeah, no, that's not what I want to show. I want to show. All right, so let's go back to this GPA model. So now I want to try and forecast spring GPA, and I'm going to use all of these variables at the same time to try and forecast it. Okay? How do I do that in Excel? Well, it's almost exactly the same. Regression analysis. Again, I'm trying to predict the values in column F here. But now my X range, basically I select all of the columns that I want to use. So now I can just grab all of these. Bottom. Okay. Okay, and now I have, these are my estimates. Okay. Right, so estimate for the intercept beta 0, estimate for beta 1, the coefficient that multiplies your AP score. So these are all the coefficients in our model. Okay. So R squared is now 62%, up from 40, what was it, 46%, I think, before. So these are models a little better, although perhaps not that much better. And then the p-values, these are telling us how significant these variables over here, AP score, SAT score, et cetera, telling us how significant they are in terms of predicting spring GPA. So if you look at them, the p-value for the fall GPA is 10 to the minus 7. Highly, highly, highly significant, right? And so, you know how when you do hypothesis tests, the typical cutoff value is around 0.05, right? That's kind of the edge of being significant. And these are all kind of hovering around that edge, so they might be somewhat useful. By including them in the model, kind of R squared from 46% and this is real data, I thought that would be interesting, right? You know, when I told you when you were freshmen that, you know, all of the stuff you come in with is not gonna, you know, it's really not correlated at all to how you do. It's really true, right? You tell me what was your SAT scores and all of that stuff, and I can't predict how I'm gonna do. But you tell me what your fall GPA is, and I'll tell you pretty accurately what your strict GPA is. Okay? But that's just an example of the mechanics of doing multiple regression. Okay. Now, first main modeling technique is going to be this decomposition method, where we first fit a trend, then a seasonal model. Right? So this kind of assumes that our time series has a trend, a seasonal component, and then what's left over is a random noise that we presumably aren't going to be able to do much with. Here's an example of a time series. I'm just curious if anyone has ever seen this before. Does that look familiar to anybody? No? Yes? All right. We're going to try and predict what's going to happen off here to the right in the future for this time series. So step one is we're going to fit a trend line to this. How are we going to do that? We're going to use linear regression. Right, so I did linear regression. It gave me an intercept and a slope and an R squared of about 0.3. All right, that shows the fitted regression line to the data. All right, so that's part of my model. That's the trend component of my model. Next thing I'm going to do is calculate what are called the residuals. Residuals are actual value minus the predicted value being given by our line. In other words, from each point, the distance from the point to the line is the residual. Oops. And that's what I get. Okay, so those are the residuals. That's what's left over in my time series after I have removed the trend effect from it. So they counted for the trend, and this is what I have left. Now I'm going to see if I can do some predicting on this. Right? So this thing looks like it's got some up and down seasonality, right? So I started a peak. Here's my peak. 1, 2, 3, peak. 1, 2, 3, peak. So there's a 3-period seasonality here. Right? That's not a real world number, right? But, you know. Seasonality is usually, you know, 12 months of the year or 52 weeks of the year or whatever, but this is a made-up example. Okay, so there are various ways I can create a model that accounts for this seasonality. But what I'm going to do is I'm going to estimate a seasonal adjustment factor for each of the 3 seasons. All right, so you have to listen carefully. So here is my, go away. Here's my original residual data here on the left, right? So then I just put the season in, season 1, 2, 3, 1, 2, 3, 1, 2, 3. So this tells us which season it is. Okay? Like cut and paste. Go away. I cut and paste the left 2 columns over here. And then I sort by season. The columns 3 and 4 are the same data except sorted by season, right? So now all of these data points in the top section are from season 1, middle points from season 2, bottom points from season 3. Then I take the average over all that season. This is the average for season 1 of all of these data points, 0.25. This is the average for season 2, minus 0.24. This is the average for the 3rd season, minus 0.01 roughly. Okay? So now, here's my model that includes both the trend line and the seasonal effect. My intercept is my slope multiplied by time period. And then I'm going to add to that one of these three numbers, 0.25 minus 0.24 or 0.008, depending on what season it is. Right? Go back to the picture. Right? If it's season 1, like this point is, I'm going to add, it gets a plus 0.25. Season 2 gets a minus 0.24, and season 3 gets a minus, or gets a 0.008. Okay, so this is my model. And this is a plot, at least up to where my cursor is, of the actual values in dark blue and the fitted values in pink. Okay. And if I want to forecast out into the future, well, I just keep, here T goes from 1 up to, looks like about 22. Then I just plug in values of T, 23, 24, 25, 26, and I get my forecast out into the future. Okay. So we've got a model, it's got a trend line in it, it's got a seasonal adjustment in it. It fits the data pretty well. And it looks like it gives a reasonable forecast into the future. Okay. Hopefully that makes sense. Okay, so now what I did is I calculated the residuals from that model. This is now my more extended model with the trend and the seasonal adjustment. Got my residuals from that model and plotted them. And now I don't see a whole lot of pattern there, at least at this point, that I think I'd be able to exploit to get a better forecast. So this is probably where I would stop. The standard deviation of these residual data gives me an estimate of the forecast error, or how variable how much error I can expect in my forecast. Okay, so in this particular example, I use a linear trend, but it doesn't have to be linear. It can be quadratic, sine waves, anything you want. Right? Just look at the plot and see what kind of function it looks like. For example, if this is what it looks like, you probably would not pick a linear trend. But if you pick the sine trend, you'd see that it actually fit the data. Okay. So we've fit a trend and a seasonal model, extracted those from the noise. Is there any way to extract anything more out of this noise? The answer is sometimes. This is where some of these time series analysis models, these ARIMA models, come into play. So far, multiple linear regression, we've seen a model that looks like this, right? Spring GPA is a function of fall GPA, SAT verbal, SAT math, AP, etc. Okay? Now you can have multiple regression models that look like this top one here. Got a linear in time, and there's also a quadratic in time trend, and there's also a sine wave as a function of time trend, and even an exponential. That's multiple linear regression. That's kind of a trend model. Here's multiple linear regression with multiple factors like fall GPA and AP score and SAT. Now here's the new one. Now check this out. This is really cool. Live T is a linear function, not of time T, not of some other variable, SAT score, fall GPA, but past values of Y. All right, so I want to predict the value of the time series Y times T. What am I going to use to predict it? The value of Y times T minus 1 is T minus 2, T minus 3, T 4. And that's called an autoregressive model. There's only one column of data, and that's Y, what you're trying to predict. Okay. Let's take a look at this. Let me see where. All right. This is that same data I have here, right? We actually were doing this data before. In the previous model, the trend and seasonal model. There's my data here. So now I want to have a model where to predict y of t, I'm going to use y of t minus 1, t minus 2, t minus 3. So I take my column of data, and I basically copy it 1, 2, 3 times. Each time I copy it, I shift it down 1 row, then I shift it down 2 rows, and I shift it down 3 rows. All right? And then I chop off the area in yellow, and then that leaves me this, right? So you'll notice, so the value, this is the value at times 4. This is the value times 3, value times 2, value times 1, right? Value times 6, 5, 4, 3. So basically, column G is the price at time t, price at time t minus 1, t minus 2, and t minus 3. Are you with me? Now keep in mind that when you do this, you're going to have to chop off this part at the bottom too. Right? So now we can just do linear regression. Go away. The way to make this go away, Jill, other than just waiting. All right, data analysis, regression. Okay, so what we're trying to predict is column G. Don't worry about it. And what we're using to predict it is all of these guys here, these 3 variables. Okay. That'll happen. All right, there's my regression. All right, so let's take a look. Here's my coefficients. Notice that they're all really, really close to 0, except for this one here, price, at time t minus 3. My p-values, they're all way above 0.05, except price t minus 3. So it's telling me I put these variables, price at t minus 1 and price at t minus 2 in there, but they're useless. They're no help at all. However, the price at time t minus 3 is really useful. Even the intercept is not useful at all. Right? So what I would typically do is I'd say I'm going to go back and I'm going to get rid of those useless variables and redo the regression only using the useful one. Let's see. Go ahead. Okay, so basically explained all of that. Okay. So this is basically what I came up with. The regression. So I get rid of these useless things and I rerun the regression with only price at t minus 3 in there, not even an intercept. And I get this model. Let's put that into, okay? So this is my new model. Price at time t equal to 1.022 times the price 3 periods ago. And that shows the actual data and the fitted data. So I had my decomposition-based model before. Trend, seasonal, adjustment factor, 5 parameters, right? Intercept slope, 3 seasonal adjustment parameters. That worked pretty good. Here I got a model that seems to work equally as well. There's only 1 parameter, right? At 1.022. It's the only parameter in this model. That's pretty freaking cool. Okay. So here now I'm trying to forecast out in the future, right? So I want to forecast this value here. So I go back 3 periods, take the actual value, multiply by 1.022, and I get my forecast. And I want to forecast this value, so I go back here, multiply by 1.022. This value here, I go back 1.022. What if I want to go further out in the future? There's no data point that I can go back to. That's 3 periods earlier, right? See what my problem is? Okay, so what do I use? Well, I go back and I use the forecast for 3 periods ago. So that's basically the point of it, right? Once you run out of data to go back to, you start using the forecast from that previous instead of the actual value. And then that will allow you to forecast way out into the future. There should be what? Yeah, so that was sort of the point, right? Let's say we have 50 periods of data. Okay, so forecast for period 51. We have that data point. We have this data point. We have this data point. But we don't have a data point 51 for time 51. So instead, we use the forecast we made, which is right here, to extend our forecast out into the future. All right. I think that's all I'm going to talk about today. This is where we'll take up next time. Yeah. So these are some pretty interesting models. If you recognize that price data that we were just forecasting, it was well done. Any questions? Okay, we're done. Okay, so I'm going to stop recording.
You should send more.